In their scenario, they imagined that Fermat was ahead 2 rounds to 1. Fermat just needs 1 more round to win. Next, the mathematicians looked at all the possible outcomes. For example, if Fermat won rounds 4 and 5, he would win the game because he would have won at least 3 of 5 rounds. If Fermat won round 4 and lost round 5, then he'd win again because again, he won 3 of 5 rounds. If Fermat lost round 4 and won round 5, he'd still win. In fact, the only way for Fermat to lose would be if he lost both of the last 2 rounds. Given these possible outcomes, Fermat and Pascal correctly reasoned the odds were 3 to 1 in favor of Fermat. Therefore, Fermat should get 3/4 of the pot and Pascal 1/4. The mathematicians calculated how a slight edge would result in one player winning more often than not. More than 300 years later, casinos like this one profit on the laws of probability.
The odds of winning in a casino are very, very small. In general, with every game, the odds are stacked against you, which does not mean that no one will win, but it does mean that any individual who plays for a reasonably long amount of time and repeatedly is almost surely going to lose. The reason the casino has a built-in edge is that every game is carefully constructed so that if you do the mathematics of it, it turns out that the casino will have a favorable expectation for winning.
The game of roulette, for example, relies on the laws of probability. The roulette wheel consists of 38 slots. There are 18 black slots, 18 red slots, and 2 green slots. If you place a bet on black, you have 18 chances of winning. But you have 20 chances of losing. The odds are stacked slightly against you. The house will win 53% of the time, and that small edge leads to large profits.
When I first started thinking about a good way to explain why casinos make money, the first thing I thought of was something called a Galton board.
With this Galton board program, Paco sets up the simulation to represent a series of bets where the odds are even.
And what we have now is a bunch of coins are going to drop from the top here, and think of yourself as a bettor as one of those coins. And each time you hit one of these pegs, you will move left or right with 50-50 probability. If you move left, let's think of it as meaning that you've lost, left for lost. And if you move right, then you win. And then you're going to bounce down to another level of pegs, and altogether you're going to make 10 bets. And you'll win some and you'll lose some, and we'll see where you end up. So we'll step through this one step at a time. So the first bettor won, then lost, won, lost, won, lost, won, lost, and ended up breaking exactly even. Let's speed it up a little bit. And now we're going to have 256 people all doing the same thing you just did, and we'll look at what the results are. And what we have is something that very much approximates a bell-shaped curve. In fact, it's approximating what's called the binomial distribution. And notice that the result of breaking even happens to be the most likely of these results, but there are many more results clustered around the middle and many fewer results at the extremes. Casinos in this situation would not make very much money. Let's go back and reset the simulation, and let's change the probability from what it was to 53% in favor of the casino. That's very much like what it would be in roulette, where the probability of winning on any of these even money bets is essentially about 53% for the casino and 47% for you. So we're going to make that small change. As I said, the odds are only slightly in favor of the casino, but let's see what happens. But notice that the center of the curve, the peak, has shifted to the left. This is very important for a casino. That means that there are still some people. Here's an individual out here who won 6 more than they lost. There's lots of people who were in the middle, but by and large, the losses have shifted to the left. The curve has shifted to the left.
By slightly skewing the odds, casinos rack up profits of over $16 billion every year. For most people, the real power of probability theory comes when mathematicians take it out of the gambling hall and into everyday life, which was something Pascal and Fermat never imagined.
It never seems to have occurred to them that when they developed this mathematical technique that allowed them to look forward into the future, that you could take it away from the gambling tables and use it in other areas of life.
One of probability theory's greatest powers is that it can help us to gauge public opinion. And this touches all of our lives.
The stakes are very high for this institution because once again the American people will be asking if we can govern.
Politicians rely on public opinion to keep track of their constituents' values.
Our major economic asset is our people. All of our policies, therefore, must be people-focused.
Public opinion influences what we see on television. And what we find in the supermarket.
Virtually every facet of our everyday lives, to some extent, is influenced through public opinion.
What is it they make Dodger dogs out of?
New products are tested, typically through surveying techniques. Also, public opinion polling, to a large extent, determines what it is that we see on TV.
Do you want milk or yogurt?
Okay, what'd you get?
Cherry vanilla.
Cherry vanilla? I gotta have peach.
We're interested, typically in this country, in knowing what a majority of the people feel. That's behind our basic political structure. That's how it is. You go about calculating it, and then the way I interpret this information statistically is I tack
in the
on
classroom,
a margin of
Kate
error to the
teaches
point
opinion
estimate.
polling.
If I subtract 6% from this, I get 69%.
But in the classroom, the true power of probability isn't always obvious.
What amounts to is the amount of information you obtain.
I went through a number of theoretical techniques, derived a lot of formulas and this and that, but I always